Let me start with something concrete, something you can actually think about. A physicist named Enrico Fermi, brilliant guy, by the way, he was sitting around in 1950 with some colleagues at Los Alamos, and he asked a question. Just one question. Where is everybody? That's it. Simple, profound, and it's still bothering us. The thing about Fermi's question is that it really does seem paradoxical on the surface. We have a galaxy, the Milky Way, with hundreds of billions of stars. That's not an exaggeration. Hundreds of billions. And we've learned in recent years that most of these stars have planets around them. Most. So if you do even a rough calculation, assuming that life arises here and there in the universe, you'd think the galaxy should be absolutely teeming with civilizations. And yet, we don't see anybody. We don't get any signals. Nobody shows up. The sky is silent. So here's what I want to do. I want to show you why this isn't actually a paradox at all. Not when you understand the physics and the mathematics. And the beautiful thing about this, and this is why I love it, is that you don't need to be a physicist to understand it. You just need to think clearly about some really basic numbers. Let's start with distance. And let me make this concrete for you because distances in space are hard to visualize. You see, in our solar system, we talk about distances in millions of kilometers. That's fine. That's comprehensible. But when we get to other stars, we need a different unit entirely. We call it a light year. And a light year is just what it sounds like, the distance that light travels in 1 year. Now, light is fast. It's the fastest thing there is in the universe. Einstein told us that. Light travels at about 300,000 kilometers per second. It's such a huge speed that we can barely imagine it. Light from the sun reaches us in 8 minutes. Think about that. The sun is 150 million kilometers away, and light makes that trip in 8 minutes. But here's where it gets interesting. The nearest star to us, not the sun, but the nearest other star, is a star called Proxima Centauri, and it's 4.24 light years away. That means that light, traveling at 300,000 kilometers a second, takes 4.24 years to get there, just to get to the nearest star. Now let me translate that into numbers you might find more familiar. 1 light year is about 6 trillion miles. 6 trillion. So if the nearest star is 4.24 light years away, that's about 25 trillion miles. Just think about that for a second. A quarter of 100 trillion miles to the closest star. Now, we've sent probes out into space. Our fastest spacecraft is called Voyager 1. It's been going for about 45 years now, and it's moving at about 17 kilometers per second, which sounds fast, right? But let me tell you what that means in terms of getting to the nearest star. At that speed, Voyager 1 would take about 75,000 years to reach Proxima Centauri. 75,000 years. The human civilization as we know it has only existed for about 10,000 years. This is a time span that's almost inconceivable. And Voyager 1 is our fastest spacecraft. We've thrown everything we have at it. It's been hurtling through space for decades. And it still only covers about 1/390th of a light year in 46 years. Now, here's the thing I want you to understand. This isn't just about being far away. This is about energy. This is about physics. To get to the nearest star in any reasonable amount of time, say, even 100 years, you'd have to travel much, much faster. Maybe a significant fraction of the speed of light. And the problem is, the faster you go, the more energy you need. And I mean exponentially more energy. Let me give you an example. To accelerate just 1 ton, to even 1/10 of the speed of light, you'd need something like 450 petajoules of energy. Now, the entire world's energy consumption in a year is about 144,000 terawatt hours. 1 ton to 1/10 of the speed of light is equivalent to nearly a year's worth of the entire world's energy supply, just to accelerate 1 ton. So if you're thinking about a spaceship that weighs, say, 1,000 tons, with equipment and supplies and all that, you're talking about maybe 1,000 times that. You're talking about incredible amounts of energy. Energy sources we simply don't have. And this isn't speculation. This is basic physics. This is F equals ma. This is the kinetic energy formula, E equals 1/2 mv squared. And there's another problem. Einstein showed us that nothing, absolutely nothing, can travel faster than the speed of light. It's not that we haven't figured out how yet. It's that the universe doesn't allow it. The speed of light is a speed limit built into the fabric of reality itself. Now, some people ask, well, couldn't you use some kind of exotic physics? Wormholes, warp drives? And the answer is maybe, in theory. But these are things that exist only in equations right now. They're mathematical possibilities. And they require even more energy. And they require forms of matter we've never detected. Things physicists call exotic matter. They exist in equations, but nowhere in the real universe that we know about. So let me put this another way. Imagine for a moment that an alien civilization somewhere has the same kind of energy source that we have. They've got nuclear power, maybe fusion power. Maybe they've got some advanced technology. They want to send a message to us. They want to visit us. They build a spaceship, and they point it toward Earth. What happens? Even at the speed of light, which is faster than anything can actually go, the message takes 4.24 years just to reach us from the nearest star. And if we send a response back, they won't get it for another 4.24 years. So the minimum time between a question and an answer is 8.48 years for the nearest star. And if we're talking about stars that are hundreds of light years away, we're talking about hundreds of years of delay. This is what kills interstellar communication, not the existence of the civilizations, not the absence of technology, but pure, simple distance and the speed of light. Now, let's think about colonization or visitation. Some people think about this and they say, well, okay, so messages take a long time. But couldn't an advanced civilization just build generation ships? Couldn't they send huge ships with people on them? And those ships would just take a long time to get to other stars. And the answer is, yes, technically they could. But think about what that means. If you're traveling at, say, 20% of the speed of light, which is already an insanely ambitious speed for a spacecraft, you still need hundreds of years to reach the nearest neighboring stars. Hundreds of years in a tiny spacecraft. The astronauts would die. Their grandchildren would die. Their great-great-great-grandchildren would die. And only much later would their descendants finally arrive somewhere. Who would do that? What civilization would commit to that? Maybe a desperate one. Maybe one that's facing extinction. But for a civilization that's comfortable, that's thriving at home, that's got everything they need, the incentive to spend centuries traveling through empty space in a small ship is almost zero. And here's something else that's important. When we think about space, we tend to think about it as empty, clean, peaceful. But it's not really like that. Space is full of particles and dust. It's incredibly cold, about 3 degrees above absolute zero. There's radiation everywhere. If you're traveling at a significant fraction of the speed of light, even the tiniest piece of dust becomes like a bullet. It becomes dangerous. The faster you go, the more damage these collisions cause. So it's not just that the distances are vast. It's not just that the energy requirements are enormous. It's also that the journey itself becomes increasingly dangerous and hostile the faster you try to go. Now, let me take this one step further. Let me talk about what scientists call the Drake equation. This was proposed by a radio astronomer named Frank Drake in 1961. And the Drake equation is basically a way of thinking about how many communicative civilizations might exist in our galaxy right now. And the equation includes several factors. Let me walk you through them because they're important. The first factor is the rate of star formation in the galaxy. How many new stars are formed every year? We know this pretty well now. It's on the order of a few stars per year. The second is the fraction of those stars that have planets. And this is something we've learned in the last couple of decades. Thanks to telescopes like Kepler, we now know that almost every star has planets. Seriously, it's not unusual. It's the norm. The third factor is the fraction of those planets in the habitable zone, the region where it's not too hot and not too cold, where liquid water could exist on the surface. This is more speculative, but if we're generous, maybe it's something like 1 in 5 or 1 in 10. Then you get to the really speculative parts. The fraction of habitable planets where life actually emerges. The fraction of those where intelligent life develops. The fraction where they develop technology and can communicate across space. And how long those civilizations survive. Now here's the interesting thing about the Drake equation. Every astronomer and scientist you talk to gets a different answer when they plug in their numbers. Some estimates suggest there might be millions of communicative civilizations in the galaxy. Others suggest we might be alone. The equation doesn't give us a definite answer because the last several factors are basically unknown. We're guessing. But I think this is exactly the wrong way to think about it, because it misses the most important constraint. The constraint that matters most is not whether civilizations exist. It's time and distance. Let me explain what I mean. Suppose there are, in fact, many civilizations in the galaxy. Thousands, maybe millions. What's the probability that two of them exist at the same time and are close enough to communicate? Think about it. The galaxy is billions of years old. Civilizations would come and go. Maybe a civilization lasts for a few thousand years. Maybe they last for 1,000,000 years. But if they're spread out across billions of years of history, and they're spread out across millions of stars, the chances that two of them are around at the same time and are close enough to reach each other, those chances become vanishingly small. This is one possibility. Maybe we're not alone, but we're all just separated by time. The aliens came and went 1,000,000 years ago. They'll come again 1,000,000 years in the future. But right now, in this small window of cosmic history where we exist, we're alone. Or here's another thought. Maybe the universe is so big and the distances are so vast and the energy requirements are so enormous that civilizations almost never travel between stars at all. They stay on their home worlds. They build radio telescopes. They listen for signals. They send messages. But they never go anywhere because it's just not practical. In fact, I think this is probably the most likely explanation for Fermi's paradox. Not that aliens don't exist, but that they're scattered so far apart, separated by such enormous distances, and facing such fundamental physics limitations that they essentially never meet. The universe is vast enough that if you wanted to hide, you could hide perfectly. You could have a thriving civilization on your home planet and never encounter another soul in the cosmos. Now, this brings up something else that's interesting. Communication. Let's say hypothetically that an alien civilization found a way to detect our signals. We've been broadcasting radio waves into space for about 100 years now. So there's a bubble expanding outward from Earth at the speed of light, containing all our transmissions, our radio shows, our television, our radar. The problem is, that bubble is only about 100 light years in radius, and the galaxy is about 100,000 light years across. So unless an alien civilization happens to be within that sphere and happens to be in the right place to intercept our signals, they wouldn't know we're here. And if they did intercept our signals and send back a reply, we wouldn't receive it for a very long time. There's another interesting thing to consider. We tend to assume that an advanced civilization would use the same kind of communication that we do. Radio waves, television, but maybe they wouldn't. Maybe they'd have some form of communication we haven't even thought of. Maybe they communicate using quantum entanglement. Maybe they use something we don't even have a name for yet. In which case, we'd be like ancient people listening for something with a radio antenna that was never designed for radio. We'd hear nothing, not because nobody's out there, but because we're not looking in the right way. And here's yet another possibility. Maybe advanced civilizations actively avoid contact. There's actually a hypothesis about this called the zoo hypothesis. The idea is that more advanced civilizations realize the dangers of making contact with less advanced ones, so they deliberately hide. They watch us like animals in a zoo, but they don't interfere. They don't announce themselves. Is this likely? Probably not, but it's worth considering, because the history of contact between civilizations on Earth is pretty dark. When more advanced Europeans arrived in the Americas, it was catastrophic for the native populations. They brought diseases. They brought violence. They brought change that nobody asked for. Maybe advanced aliens learned that lesson too. But here's what I think is really important to understand, and this is why I love this problem. We don't need to invoke any of these exotic explanations. We don't need aliens to be hiding. We don't need them to be communicating in ways we can't detect. We don't need cosmic conspiracies. All we need is physics. All we need is the vast distances of space and the speed of light. The universe is old, about 13.8 billion years, but it's also unimaginably large. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. The distances between stars are so vast that light, the fastest thing in existence, takes years just to go from one star to the next. Given these numbers, given the energy requirements for interstellar travel, given the time it takes for any signal to cross those distances, it's not surprising that we're alone in our little neighborhood. It's not surprising that the sky is silent. In fact, if anything, I'd say we're incredibly lucky to even exist on a planet like Earth, around a star like our Sun, at a time like this, when we're aware enough to ask these questions. The odds of that are already pretty small. Now, I want to leave you with something. A way of thinking about this problem that I find beautiful. The Fermi Paradox, this question of where the aliens are, doesn't show us that we're alone in the universe. What it shows us is something more subtle. It shows us that the universe is structured in a way that makes meeting almost impossible. Even if life is common, even if intelligence is common, the speed of light and the vast distances act like a filter. They keep civilizations isolated. This, to me, is a profound answer to Fermi's question. Not, where is everybody? But rather, everybody is far, far away, and the physics of the universe makes it nearly impossible for us to find each other. It's a lonely answer, in a way, but it's also a true one, as far as we can tell. And that's really the point. When you look at this problem, really look at it, you see that it's not a mystery in need of exotic explanations. It's a consequence of physics. It's a consequence of the fundamental structure of the universe. And once you understand that, once you really get it, Fermi's question becomes not strange, but almost inevitable. The universe is big, really, truly, unimaginably big. And the speed of light is slow in comparison to those distances. That's all you need to know to understand why the sky is silent. That's all you need to know to understand why the aliens haven't arrived. And in a way, that's the most elegant answer of all.